Hello everyone, welcome to our new session of a fluid mechanics subject. In this session, we will see about the two examples that is based on the Hagen-Poiseuille formula and which is for the flow of a viscous or the laminar fluid which is flowing through the circular pipe. As we have already seen about the a long derivation on this basic formula about the pressure head loss in the circular pipe. So let's start some of the example on the same. In the examination point of view, there is one question regarding this flow of viscous fluid through the circular pipe. Either it is in the derivation form that they can ask you in the derivation form as the Hagen-Poiseuille formula, or they can ask you in the examination format with examples. So let's start one example and let's see how we can solve the example that is totally based on this formula. Here it is the one example. A crude oil, we are having a crude oil having a viscosity of a 0.97 poise. It is the viscosity of 0.97 poise and it has the relative density of 0.9, which is flowing through the horizontal circular pipe. Just remember one thing, this example is only for the circular pipe. Okay. So fluid is flowing through the circular pipe which is having a diameter of 100 mm and the length of 10 meter. Calculate the difference of pressure at the two ends of pipe. We need to find out difference of pressure or the drop of pressure, that is P1 minus P2 at the two section of pipe if the 100 kg of oil is collected in the tank in 30 seconds. This one is your mass flow rate, that is 100 kg of oil which is collected in a tank in 30 seconds. So here it is your given data regarding this examination as mu, that is your viscosity and which is given in the poise. So always we need to convert this all the parameters in our SI format. So this poise is 0.97 poise, which is your viscosity. So to convert in SI unit, that is Newton second per meter square, we need to divide this term with divided by 10 so that you can have an viscosity in SI unit, that is 0.097 Newton second per meter square. Next thing that is given us, which is relative density, but we don't need a relative density, we need a pure density. So to convert this relative density into the pure density, we have relative densities, it is 0.9, and by multiplying this 0.9 with the 1000, we can have a density, that is rho, density that equals to kg per meter cube. So this one is your relative density. So first of all, convert this relative density into density and it will be in the kg per meter cube. Okay. The next thing that is given us, which is the diameter, that is in mm. So convert it into meter divided by 1000. So 100 divided by 1000 and that is 0.01 meter, which is the diameter of your circular pipe. And the length of pipe, which is 10 meters, so it is in SI unit. Mass of oil, that is 100 kg, here it is the mass of oil, that is 100 kg, and the time, that is in second, T, which is in second, and calculate the difference of pressure. We need to find out difference of pressure, that is P1 minus P2, that we have to find. Okay, so this type of questions they can ask in 4 marks or in 7 marks. Okay, so let's find out this a drop of pressure. Okay, so as the a drop of pressure for the laminar flow is given by, this one is our drop of pressure, which is already we have seen in Hagen-Poiseuille formula in our previous session, that is P1 minus P2, that equals to 32 mu, that is viscosity, u bar, that is average velocity, into L divided by d square, where u, that is your average velocity, which equals to q divided by area, where q, that is your discharge or the volumetric flow rate. Okay, so First of all, we need to find out this u bar, that is average velocity, and put this value of u bar in this equation. Okay, so let's find out the u bar, but before that, we need to again find out this q, that is your discharge, and it is given us that is 100 kg of oil is collected in a tank in 30 seconds. So here it is your kg per second, that is mass flow rate. Okay, which is your mass flow rate, that is given mass flow rate 100 kg per second, but we need this one is in volumetric flow rate. A volumetric flow rate, because the unit of volumetric flow rate, that is meter cube per second. Okay, so by we can see that over here 100 divided by 30 and density into q. So we have density, that is 900 into q. So this mass flow rate, that equals to density into q, and it will gives you the volumetric flow rate, and there will be in meter cube per second. You can see that over here, that is kg per second, which is your mass flow rate. To convert this mass flow rate, we need to compare this mass flow rate with the density and q. So you can find that unknown parameter, which is q, that equals to 100 divided by 30, and this 900 is goes toward the left side, so it will be in 1 divided by 900. So this and this will be cancel out, so 1 divided by this 270, and it will be your in 0.0037 meter cube per second. So this one is your volumetric flow rate. This is nothing but volumetric flow rate, which is in meter cube per second. So we need this q, over here. Okay, so put this q in that equation, which is your u bar, that equals to q divided by area, and the q, that is 0.0037, and the area of circular pipe, that is pi by 4 d square, where d, that is given, which is 100 mm. If you remember, that was given in our example, which is 100 mm, and we had converted that 100 mm into meter, and that will be your 0.1. Okay, so the answer of this average velocity is 0.471 meter per second. That is your average velocity. Okay, so now you are having this value of average velocity, so simply you can put this into pressure drop. But before that, we need to confirm that this one is your laminar and the viscous flow. So for the confirmation, we need to find out the value of Reynolds number. If your Reynolds number is less than 2000, then and then we can say that this flow is laminar flow. So let's find out the Reynolds number, and the equation for the Reynolds number, that is Re equals to rho Vd by mu, where rho, that is the density of fluid, that is 900, V, that is the velocity, it means u bar. In the previous slide, at the end of that slide, we had already found that 0.471 meter per second, that is your velocity, d, that is your diameter, mu, which is your viscosity. Okay, so by putting all the values in this equation, we can find out the value of Reynolds number, and the Reynolds number is again less than 2000, so that we can say that this flow is laminar or the viscous flow. Because of this viscous flow, as the Reynolds number is less than 2000, the flow is laminar, so that you can find that this pressure drop and put this equation of pressure drop, which is shown in this slide earlier, this one. Okay, 32 mu u bar L d square, 32 mu u bar L d square. So 32 mu, that is 0.097, u bar, that is your average velocity, L, that is the 10 meter length, and the d, which is the diameter of 5.1 square. Okay, so by multiplying and dividing this whole value and simplifying this equation, we can have, and the answer of the pressure drop, that is 1462.28 Newton per meter square. Okay, so this one is your pressure drop. So if you're multiplying this 10 raised to minus 4, and it will be your Newton per centimeter square. If they are asking in examination that find out the pressure drop in the Newton per centimeter square, so first of all you need to find out this value, which is always in the form of Newton per meter square. This answer of this formula, it will gives you in Newton per meter square, that is in SI form, and convert it into the Newton per centimeter square by multiplying this value 10 raised to minus 4. Okay, so it will gives you 0.1462 Newton per centimeter square. Okay, so here it is the end of this example, which is in 4 to 7 marks. Let us see one more example based on this Hagen-Poiseuille formula, and the oil of viscosity, that is 0.1 Newton second per meter square. So it is already in SI unit, that is Newton second per meter square. Relative density is 0.9. So first of all convert the relative density by multiplying the 1000. Is flowing through the circular pipe a diameter of 50 mm. So 50 divided by 1000, and that will be in your meter. Okay. And the length of this pipe, that is 300 meters. So we have a diameter 50 mm and the length is 300 meter. The rate of flow, just note it down. Here it is the rate of flow fluid throughout the pipe, that is 3.5 liter per second. So simply you can convert this liter by dividing this 3.5 with the 1000, and you can have an answer in meter cube per second. So we need a discharge, remember one thing, we need a discharge in meter cube per second. Okay, so here it is the rate of flow, that is in a liter per second. Find the pressure drop, which is your P1 minus P2 in the length of 300 meter, and also just remember, first of all, find out pressure drop at the length of this 300 meter. Second thing, also the shear stress at the pipe wall. So here it is, we need to find two of unknown parameters. First of all, pressure drop, and second is shear stress tau. So here it is your given data. You need to write down in this format, that is mu, that equals to 0.01 Newton per meter square. Relative density, that is 0.90. So by multiplying this 1000, here it is 900 kg per meter cube. Okay, diameter, which is 50 mm, so divided by 1000, it will be your 0.5 meter, 0.05 meter. Length is 300 meter. Discharge is 3.5 liter per second. So by dividing this 1000, and you can have answer in the meter cube per second. So we need to find out rate of flow, or it is called volumetric flow, that is meter cube per second. Okay, so we have this discharge. First thing, that is to find P1 minus P2, that is pressure drop. Second thing, to find out shear stress at a pipe wall, at the periphery, inside periphery of the pipe wall, that is a shear stress tau. Okay, so two unknown parameters we need to find out. So first of all, let's find out pressure drop, and the value of pressure drop, that is 32 mu u bar L divided by d square, where u, that is your average velocity, and the equation of u, that is q divided by a, as we have already discussed in derivation and also in previous sum. So just put the value of q, that is 0.0035, and the area, that is pi by 4 d square. So the value of d, that is 0.05. So after the simplification of this calculation, here it is the answer for average velocity 1.782 meter per second square, that is u bar. So simply put this value of u bar in this equation. But before that, as we need to confirm this flow is laminar or not, so first of all, let's find out the Reynolds number, that equals to rho Vd by mu, where rho, that is the density in kg per meter cube, V, that is average velocity over here, that we are already find out, d, that is diameter, which is 0.05 divided by mu, that is 0.1, that equals to 801.9. So it is less than 2000. So if your value is less than 2000, then and then we can say that this one is your laminar flow. So the laminar flow, for the laminar flow, we need to find out this pressure drop, that is P1 minus P2 into 32 mu. Put this value in this equation, 32 mu This one is u bar into L divided by d square. So after the simplification of this equation, answer is 684288 Newton per meter square. So this one is your final answer, that is Newton per meter square. And if you need to find in Newton per centimeter square, so simply multiply with the 10 raised to minus 4 and it will be your 68.43 Newton per centimeter square. So here it is our first answer for the pressure drop. So first of all, if you need to find out pressure drop in this equation, firstly find out this u bar, which is your average velocity, and the second thing that is to confirm this flow is the laminar flow. So the value of Re is must be the less than 2000. Let's find out the second thing, that is the shear stress at the pipe wall. So suppose here it is our pipe, here it is the center line of pipe. So when your this R, if you remember our previous session, this one is your R, that is the radius of elementary area, and over here it is your capital R, that is the radius of pipe. Small r, that is the radius of elementary ring which is assumed by us, that is the radius of this ring, that is small r, and capital R is the radius of this pipe. So the shear stress, we need to find out shear stress at a radius of small r, okay, and it will be in the form of this equation which is already discussed in a previous session, that the tau that equals to minus dp upon dx, del p upon del x into r by 2, okay. But the shear stress at the pipe wall, and the pipe wall at the radius of pipe wall, that is capital R, so the R is replaced by capital R, because we need to find out shear stress at a pipe wall, and the radius for the pipe wall, that is capital R. So the tau that equals to del P minus del P upon del X into R by 2, okay. So first of all, we need to find out this term minus del P upon del X. So here it is minus del P upon del X. So this del P upon del X, that is nothing but the difference of pressure and the difference in the X direction. So difference of pressure minus P2 minus P1. So a negative sign will be multiply inside. So it will be your P1 minus P2 divided by X2 minus X1. So this X2 minus X1, that equals to L. Okay. So we have the value of P1 minus P2 over here. Here it is the value of P1 minus P2, 684288. 684288. So here it is the value of P1 minus P2 divided by this L. So it will gives you the answer for this P1 minus P2 divided by L, 2280.96. Okay. And the R by 2, that is diameter by 2. So the diameter is 0.5 and 0.5 by 2, that is 0.025 meter. So by putting these two values in this equation, first of all del P upon del X, it means this one is first, and by putting this second value in this equation, we can have the answer of this shear stress, that is in Newton per meter square, which is 28.51 Newton per meter square. So this type of examples they are asking in our examination, that is to find out the pressure drop in our viscous fluid, which when your fluid is flowing through the pipe, and secondly they can ask a shear stress at any end of pipe wall. So I hope you are getting this and you are understanding this session. That was all about today's session. Thank you so much. So you need to write down these two examples by yourself and submit it towards Google Classroom. Thank you.